Uh, okay, so now it's on. Okay, so welcome to another edition of the Priberam Machine Learning Lunch Seminars. Today we have Ben. Ben was a colleague of mine during my PhD, great colleague, great friend as well. And he's now a postdoc researcher on INESC-ID, and he's going to tell us about what's in a speech token. Then the floor is yours.
Okay, well, actually, I wasn't sure that I was supposed to say what's in a speech token. I thought I was just supposed to ask all of you, because the truth is I don't really know. Which is, I mean, that's not exactly the case. I've been looking a lot into trying to understand what's going on to discrete speech tokens, and let's just say that this presentation ends with a question mark, not with a period. So, of course, to start off, there's an obligatory slide, just like in the first sentence of every paper you've read in the last 5 years, saying that language models are good now. Observe this. They have a function that goes beyond simply being next token predictors or things that allow you to assign a numerical score to a sentence. They're things that you can use for practical tasks. And they're also standardized to a greater degree than they were before, making it much easier to use other people's results to iterate on things that have already been developed. But the majority, not all, but the majority of these developments have been focused specifically on text. And speech is a different beast. It's a much richer signal that includes a whole lot of other things that you're not going to find in text. The sequences, basically, no matter what you're going to do, are also going to be much, much longer than the ones you deal with in text. Most speech models these days accept an input audio that is 16 kilohertz, 16,000 examples per, not whatever you want to call them, per second. And speech encoders typically produce output that is at 50 hertz, 50 tokens per second, sometimes less, but often 50. And there's no obvious way to segment it into meaningful units without doing some more sophisticated modeling. So in this talk, I'm going to talk about one particular technique that you can use in order to integrate speech representations into a text language model. It's not the only technique, but it's the one I decided to make this talk about. And that is discrete speech units here. I believe I took this this image from a paper that I'm going to discuss a little bit later. But the general idea of this is you have some speech data. You can run a speech foundation model, an encoder essentially, something like Hubert, wave to vec. The specifics matter a lot in terms of what the representations encode, but in terms of the architecture, the point is it's a thing that outputs you a sequence of vectors that provide some sort of representation of the input, some continuous features. On top of that, you can learn a kind of clustering. And this is where people end up using the notion of tokenization. You train a k-means model essentially on a lot of these continuous frames that came out of a speech model. And then when you want to use this in conjunction with your text language model, you map each frame to the ID of the closest centroid. So essentially, you can turn a whole lot of speech into a sequence of integers, and each of these is essentially a token type, just as the token types that are encoded in your text language model are. And this makes the problem of extending a language model fairly easy. Let's say you have got a text language model that has an embedding matrix with 32,000 rows. You can just add more rows to it and define them as belonging to these speech types. And then by training for longer, you can make them so that they're actually good. Because you need to find a way to initialize them. But while initialization used to be a problem that people were concerned about, in practice, it doesn't seem to be such a problem to just do a random initialization, maybe with the mean of the existing embeddings, and then train for a while. It doesn't cause your text representations to collapse, and it does allow you to learn good representations of the speech on the side of the language model, as opposed to on the side of the speech foundation model. So as a case study in this, we released a paper last year called Spire. And the idea of Spire was to take Tower, which is a a model that does translation related tasks and also general language modeling tasks that originated in Lisbon. Many of the people involved in the project are in the room right now. I am today. And the idea is that on top of that, can we make it so that it doesn't just do, text things, but also speech things? By adopting sort of a similar paradigm to the paradigm that was used to create Tower, where the idea with Tower is you take Llama 2 and you do a whole bunch of extra pre-training of it using text in other languages, and then you do instruction tuning to make it good at particular tasks. We, in turn, took Tower, so it's building another layer on top of this where it does some speech, and then you instruction tune it in order to build a model that can handle concrete tasks. In our case, speech recognition, still text machine translation, but also speech to text translation. Later on, we found out that actually you don't really need the continued pre-training stage, perhaps, as long as you improve the quality of the instruction tuning data. But that's sort of orthogonal to anything else in this presentation. Uh, and the point is you can do this and it works all right. So above the middle line there are ASR results on a number of different corpora using both Whisper, which is a model that a lot of people use for speech recognition, as well as other models that are specialized either in speech translation or in speech language modeling. These numbers are word error rate, which means lower is better. And their four corpora represented. LibreSpeech Clean and other are both read speech from audiobooks. Fleurs is it's the companion to Flores, which is a multi-parallel translation corpus with sort of, I don't know what the actual source of them is, but they all look like sentences from Wikipedia articles. So these three are all fairly high quality speech. And then Vox Populi is recordings of speakers in the European Parliament. So there's a lot more accented speech and speech that is a little bit less rehearsed. Not totally like free conversational speech, but a little bit less rehearsed than reading an audiobook. Uh, anyway, but that's all kind of preamble because I wanted to interrogate a belief I had that I wasn't actually sure if I had enough evidence for. Namely, so if you use discrete audio representations as opposed to other approaches where you're connecting the speech encoder to the language model through like an MLP or something, basically through dense layers. My belief was that if you use discrete things, you can have an easier time shortening sequences, and this will make your life easier in the long run because language models can handle much longer sequences than they used to, but still audio is just in general a much uh, it produces much longer sequences than text. So the thought was that by adopting this discrete view of speech, we can apply some kinds of techniques that are applicable to text to our speech representations, and they'll allow us to train models that are more efficient. I mean, one of these is one that's not necessarily actually used for text, which is deduplication. The idea essentially that you've got a sequence that has a lot of repeated consecutive elements. And this happens all the time when you're dealing with speech because adjacent frames are very similar to each other because they refer basically to a very, very small time window. So you can reduce it very quickly. Honestly, I don't know anybody who does not use deduplication if they're using discrete speech units, and I don't have any very good baselines without it. I think one of my master's students might have tried at one point, but there wasn't anything too interesting there. But the more sort of realistic idea of shortening sequences that does originate in text is the idea of using some kind of subword tokenization. So, for example, byte pair encoding, which, I mean, I challenge you to find a large text model that is not using byte pair encoding somewhere in it. The idea is that you start out with a small vocabulary of atomic units. In text, this would be characters, but you could also think of doing exactly the same thing with a sequence of discrete speech units. And you incrementally increase the vocabulary by finding the most common bigram and merging it into a new unit. And then updating the bigram counts, and going on until you reach some desired vocabulary size. Uh, you can see as it so incrementally learns to build meaningful units, essentially, like the out of this large, out of this, in this case, very, very small corpus of units. So you can do this, and at the cost of increasing the vocabulary size, you make the sequence much shorter. Because in the original version here, it's totally unsegmented. Every character is a separate element. And as you learn larger units, the sequence gets shorter. And thus you would think easier to work with. But let's actually think about what happens empirically to our sequence lengths when we apply this to speech representations. So the base frequency here is what I mean is Hubert large produces 50 hertz output. So for every second of audio, you're going to get 50 discrete speech tokens before you apply any deduplication. Empirically, every time I've ever trained a model with this, after you apply deduplication, you get it down to about 35 hertz, right? So that's still a lot, units that are much smaller than words. Based on this ballpark number, we speak maybe 2 to 4 words per second. If instead of doing deduplication, you do deduplication and then you train a byte pair encoding vocabulary over that, what you get is certainly a lot lower frequency than that. We're down to, I don't know, 16, 17 hertz. On the other hand, a different idea. What if instead of doing any kind of text level tokenization scheme, we just look at the frames that come out of our speech encoder, right? They're at 50 hertz, and we just do mean pooling on pairs of units. So the pooling width is 2, the stride is 2, so you're approximately reducing your sequence length by half, and then you're deduplicating on top of that. So this essentially is a way to reduce your frame rate by 2 without having any extra parameters. We'll see later whether it actually works or not. But you see, it's not quite as efficient as this byte pair encoding we have. But whereas byte pair encoding got us down to 17 hertz at the cost of a ton of new parameters, because we need to learn embeddings now for every speech subword that has been learned. For this, the cost in terms of parameters is 0. Mean pooling does not have any parameters. And then if we use mean pooling, but instead of using a width and stride of 2, we use a width and stride of 4, you see that we're already actually down to around 10 hertz, which, that's getting to the range where these are around the same level as, phones or characters, perhaps, assuming we've got 2 to 4 words per second we're speaking at. I don't have anything more than an intuitive idea about how close these are to characters, actually, but it seems like it's in the right ballpark, at least, that we've now turned this into something resembling like byte T5 in terms of the level of representations it might encode. But yeah, regarding this efficiency, so if we're going to compare training byte pair encoding on speech units versus training them on text units, it's actually a little bit more challenging as a task, which initially was a little bit surprising to me. Training, setting the vocabulary size fixed. So this is the same number. Actually, it's not the same number of merges precisely, but you're ending up with the same vocabulary size at the end. Byte pair encoding does not actually get you units that are very short. You're only getting 2.2 DSUs per token in the input. Whereas if you trained a 32K vocabulary for byte pair encoding on the ASR data that I used for training the models in the experiments I'm going to show later, you see that the units it produces are actually quite a bit larger. And, byte pair encoding is based on finding frequent pairs of bigrams and iteratively merging them. But I suppose what we're learning here is that if we set a speech token vocabulary whose size is in the thousands, and the most frequent bigrams are going to be less frequent, and the distribution of them is probably going to be a lot flatter. So like the first merge, if you start with like a distribution of bigrams in English text or something, is probably going to be something that occurs all the time. Like it's going to be like the TH in the or something. And the is the is like 6% of English text or something. So by doing just this one merge, you're actually having a big impact a whole lot of the time. But with this flatter distribution, finding the most frequent merge, it's just not that frequent. It's not going to change that many sequences. So it's, in terms of the parameters you add, it's actually very inefficient in terms of how much shorter you make the sequence. And the other issue, so I ran an experiment to try to compare directly whether byte pair encoding can help you to make sequences shorter. And I mean, it works. I trained the model, but you take a little bit of a hit in terms of performance compared to not doing that. Is it a little bit faster to train? Yeah, it's a little bit faster, but it's not that much faster. And the shortened sequences come at the cost also that your softmax layer is larger. So every individual decoding step is more expensive than it used to be, in addition to having more parameters. And the results are a little bit worse on all the corpora I tried. So the comparison here is between taking tower base, not the Spire model that I briefly mentioned earlier, and then instruction tuning it on a lot of audio data for different tasks. And then using the same data again with tower base, but instead of using just an atomic DSU representation, using these BPE units that I trained on it. And yeah, it didn't work as well. And I allude to dumb reasons here. The dumb reasons are entirely implementation based, which is that people tend to rely on code bases that are fairly old for doing tokenization. And I imagine most people working on language models in general want to think about tokenization as little as possible. They want to think about their language models as generating sequences of words and not thinking about this icky thing that cannot be fit into our end-to-end differentiable objectives. And the result is that they don't actually include very many features in most libraries for making things easier. So if you want to extend a byte pair encoding model with additional merges, intuitively this is very simple. The process I described for training a byte pair encoding model earlier, essentially you've got a model, you find the next most common merge, you add it. You have a new model that consists of the old model plus one additional merge. But in practice, with implementations, you cannot take an old model and add new merges to it very easily. It required a lot of hacking in sentence piece to get it to work a little bit better. And more recent models that you'll find on Hugging Face do not even use sentence piece in the backend for their tokenization. They use other libraries that I've never actually managed to get to work for this at all, which is the reason why I have a separate table, because the results here are not completely comparable. I found models that were much nicer to work with for training than Tower Base in terms of results, and they worked very well with pooling. But the thing is, I could not figure out how to extend the tokenizers for models from the Quen family. LMT it's essentially applying the tower approach, but with Quen 3 as a base. So, and it also supports a few different language pairs than the tower family does. But anyway, so previously I showed essentially a decline when using BPE that comes at a very large parameter cost. Here I'm showing there's still a decline with this pooling approach, but at least there's no parameter cost. And in practice, the pool 4 configuration here is more efficient in terms of how much it shortens the sequences than just using BPE. So I guess that's the most solid conclusion I managed to come up with after I wrote my abstract and decided I need to actually get some results now. It's that, yeah, I would not use BPE with discrete speech tokens. It seems like this putative advantage of using discrete tokens is maybe not such an advantage at all. Uh, Moving on. So there's another line of research which tries to sort of quantify how good a specific speech tokenization is by measuring how well aligned it is to linguistic units. And it makes sense that this is something that you might expect. Like, whether we're working with audio or we're working with language, we are working with a system that essentially consists of items from a discrete vocabulary that we combine in interesting combinatoric ways. The speech signal itself is continuous, but when we are communicating in terms of long sequences of discrete units. phones or phonemes, whatever you want to call them. The usage seems a little bit fuzzy between these two terms in the ASR literature, but so what we're going to try to do now is look at different discrete speech tokenizers and look at how nicely the units that come out of them actually do align to phoneme labels. And in order to do this, we need to make some data. There are corpora out there that consist of time-aligned phones along with audio signals, but most ASR corpora do not have that. They just have the speech signal and the text as it would appear. But there are forced alignment tools you can use in order to induce this alignment from such ASR output. And then because we know the frame rate of DSUs before we deduplicate them, it's trivial to align the DSU sequence to this other time-aligned thing we have. Intuitively, it looks kind of like this. So at the top, we've got a waveform there. On the level below that, you can see a time alignment between the waveform and the words of the transcription. This is somebody speaking a story in LibreSpeech Clean, I believe it is. You can see on the level below that there are representations of the phonemes. So we're not encoding the spelling of how English works, but these are units that stand for units of pronunciation of English, essentially. And then on the level below that, we have the IDs of different discrete clusters that were learned by one of the discrete speech tokenizers I used. Looking at this, it's not super readable, and it looks honestly kind of arbitrary and random. Especially there's this 1499 token that is just appearing everywhere for long stretches of time, that including the part at the beginning before the person is even speaking. So it's probably not encoding a unit that is very particularly phonetic in what it represents. And also there are several different units in quick succession around the point where the S is being pronounced at the beginning as well. So it's not super clear just from looking at this, but if you're going to actually compute some statistics about it, you can come up with a different story. Although to get into how I'm going to tell the story, first I want to tell you what I actually did for experimentation here. So I fixed my tokenizer training with some fairly common values. A discrete speech unit vocabulary of 5,000 types, same as was used for Spire, and extract all of the continuous representations from the 22nd layer of Hubert Large. This is kind of a magic number, but it's a magic number that is used in quite a few papers. And then essentially, instead of picking a fixed amount of data to train a tokenizer on, you train it essentially until the k-mean centroids stop moving. They will eventually come to some kind of local minimum. When they've moved by less than some epsilon, you decide that you are done training your tokenizer. And what's different between the settings, essentially which data to train on. Common Voice is read speech collected by the Mozilla Foundation. GigaSpeech is YouTube videos and podcasts. MLS is quite diverse, and SPGI is like financial calls. In addition to that, I use the Spire tokenizer, which is a mix of MLS, Common Voice, and Vox Populi, but with slightly obscure details about how precisely it was trained. And then I take that and I instruction tune some text language models to do ASR, conditioned on units from these vocabularies. So what you can see using LMT 1.7 billion as your base text model to which you've added these types, there is a little bit of a difference between the different tokenizers, and none of them do quite as well as the Spire tokenizer. However, I don't know, 1 point of word error rate, maybe not the most important difference in the world, but if you look instead using a smaller model, the differences get quite a lot bigger in the performance between these models. And to be clear, these two were trained on precisely the same data, but some of the tokenizations had a much harder time dealing with this encoding. I mean, smaller models are more limited, but why should this be more challenging than than it was for the larger model precisely? And here is where I started to look first at phone purity. So this is a fairly commonly reported metric for discrete speech unit types. The idea is for every cluster, so there are 5,000 clusters in our case, you want to find what is the probability of the phone type that gets the most probability conditioned on that cluster. So if every cluster it were completely deterministic which phone was mapped to it, then this max p would always be one. Uh, and then so you compute that for every cluster, and then you take the expectation of that over cluster frequencies. Uh, Anyway, that'll give you a number between 0 and 1, I do believe. And what we can see here, again, is not a very consistent story. This doesn't seem to have very much to do with the variation between tokenizers in the ASR results you can get. Uh, the caveat, of course, is that these are phone labels that came from forced alignment. They're not annotated by a human. But yeah, hard to say exactly what's going on here. I mean, it's interesting also so if you look at the difference between corpora here, one explanation is that I used the same settings for forced alignment regardless of corpus, but which meant I was using an American English acoustic model for everything, which is going to map pretty nicely, I guess, for LS Clean, but much less well when the speakers are members of European Parliament, as in the case of Vox Populi. Uh, yeah. And after that, I tried to find a whole lot of things that would explain essentially why some of these tokenizers perform much worse than others in spite of seemingly providing similar phone purity. Uh, and yeah, this is an incomplete list of negative results. I tried a number of things. One of them is a notion that comes actually from people thinking about how best to train BP models for text. And the idea is if you want the type that occurs more or less frequently than 95% of the items in your vocabulary to have a fairly large number of occurrences. Uh, this didn't tell me anything when I computed it. Uh, you might want to look just at the token sequences that you're training the model on and ask what's the entropy of the sequence. No meaningful differences between the models that I could find. Also computing the entropy per cluster. So instead of like where with purity you're really looking at like what is the probability given to the most aligned phone. This is if you're doing the per cluster entropy, you're trying to find what's the uncertainty about the identity of the phone conditioned on the cluster identity. And then there are a number of metrics that might allow you to find agreement between clusterings. So adjusted rand index is essentially a way to compare two different clusterings and see whether they represent the same things. Basically, if you can replace the labels of one with the labels of the other in a deterministic way, you're going to have a high score. And if it's completely random, you're going to have a score around 0. In this case, what I actually found is that the tokenizers were actually quite different from each other, but not in a way that lent itself to analysis on this timeline I had. Uh, so yes, this is me saying, I don't know. Uh, yeah, I had a number of future ideas. They're not necessarily connected to the precise mystery here, but they're related to other things a person might want to look at if they got interested in discrete speech representations. So one of them, for example, perhaps you've heard of fishing for Magikarp. So there was an influential paper from Cohere a couple of years ago uh, that observed that due to artifacts of how tokenizers were trained, a lot of large language models contain types in their embedding matrices that were never actually seen at training time. The result is basically you've got an embedding matrix that has a bunch of entries that are essentially uninitialized in it. And if you pass these entries to a model, you can get it to engage in some unexpected behavior. The reason for the title of this paper is because I can't remember which model it was, but the embedding matrix contained a type that was just solid gold Magikarp or something. So empirically, I've looked at some of the models I've trained, and there are some discrete speech types that are vanishingly rare, like maybe only one occurrence in 30,000 hours of audio or something. So I know that they exist. The problem is that it's harder to sort of induce bad behavior from a model this way because I don't have a nice way to sort of perturb an existing audio file such that the tokenization contains this type. So it's a little bit harder to do some kind of adversarial attack on a model to get it to generate something bad based on this than it would be with text. Uh, Another paper that I remember looking at sort of toward the end of my PhD was one where they looked at the representations in the embedding matrices of text models, both encoders and decoders, and they found that they could train a probing classifier to predict with at least interesting results how the word corresponding to that embedding is spelled. So it's a finding that there is actual character information that is encoded in subword types. Uh, if you train a model on speech or on text and discrete speech for well enough, are you going to encounter similar information here where you can be conditioned on the embedding for some large subword of text? Can you predict how it is spelled in terms of discrete speech tokens? And I'm gonna guess, I don't know, it's probably not the most interesting result, but I'm kind of curious. Anyway, that's actually all I had for you today. So thank you for your attention. Please let me know if you have answers to any of my questions.
Thank you, Ben. I think there are some questions in the chat so Vlad asked a question. Is does deduplication remove some timing or synchronization information that may impact certain downstream tasks, especially in a more model setting?
So yes, I mean, so the place where deduplication is really a problem is if you're not trying to just predict text conditioned on speech, but if you're trying to predict speech, where you might want this duration information. I suppose also like if you wanted to do like some kind of emotion classification, or maybe I don't know, are people going to say things for longer when they're really bored? Like that's something you lose when you deduplicate, perhaps.
Another question was on slide 10.
Uh-huh.
To what extent does VPE performance depends on initial number of discrete tokens configured, and how should we pick this number?
Uh-huh. So
And clusters in the means?
yeah, so right, yeah. So I've seen for the most part numbers that are in the same ballpark as 5,000, basically between 1,000 and 10,000. If you select fewer clusters, then I think you're going to get better BP efficiency, just because the initial alphabet you're starting with is smaller. Uh, I did not rigorously tune this number because these are kind of expensive experiments to run if you're actually training an LLM downstream of it.
You showed a slide earlier that showed an alignment between the DSUs and the phones.
Yeah.
I'm thinking, looking at it now, have you considered doing an experiment where you try to match the number of DSUs to approximately the number of available phones and see if those line up better?
So I haven't run that experiment. I so you're getting to an interesting point, which is that I just assume this is not going to work, but I don't have the empirical backing for it. It's like my assumption is that these things work a little bit better when you over parameterize them. By select and then everybody seems to select numbers in the thousands at least, and there's no language on Earth that has a phoneme inventory that big. But yeah.
Yeah, go ahead.
Yeah.
Like in all the tasks we've been doing,
Mhm.
the linguistic is more important, but in some tasks of speech, the language,
Yeah.
you may use speaker information or
Mhm.
like prosody stuff like that.
Yeah.
I was wondering what you think about speak token for this kind of things.
Everybody seems to think they work very badly for them. And yeah, it's not where I would start if I were working on this kind of thing.
Other questions? Oh. Looking at the back.
So one thing I'm curious about is all the like suppose that you change the domain of your text or you have like a different set of speakers, different
Right.
context backgrounds, whatever.
Mhm.
How much of a problem is it the gaming step where you are the initial clusters? Are you going to see a big degradation in the clusters that you are using just on that step?
I would guess yes. Like I was getting in a very rough sense at that kind of by trying different corpora, but I haven't studied the effect too rigorously in that sense. But I would guess that the domain robustness is not very good. Uh, based, for example, so in the Spire paper and my experiments to try to figure out what was working and what wasn't with it, one thing I saw, for example, is like on Fleurs, we were doing very, very well. Uh, but on Covos 2 for translation, the results were uh, like much worse. So there are places where we were getting similar results to seamless on Fleurs, but you change the audio domain and it's quite a much larger problem. So yeah,
But is it because of that to do with the clusters or with something else?
I would guess it has a lot to do with the clusters. Yes. I mean, so like I don't think the translations itself are substantially more difficult. And so the way you would check this would be, so the same model can do text translation, and you look at how well it does given like gold ASR to predict the translations. It should be much better, and I believe that's what we did indeed see. We were fine as a cascaded model, but on direct it was a problem, which meant yeah, the clusters themselves are suffering.
So I have another question. I was looking at the slide that we have right now, and you see 1499 very often.
Yeah.
And often it's like a silence,
Uh-huh.
but there's also in the middle of the story. If you 1499,
Yeah.
do you have any idea about what is going on?
So yeah, if I see the first few things, I would assume it's just encoding some silence or maybe some very particular background noise that's occurring in some places or something. But I'm not actually sure. So uh yeah, I couldn't tell you.
I was wondering if it could be any outlier that's the science that gets or something.
Yeah. Like I mean, I'm not thinking it's an outlier per se, because as far as I know, the model translated this or transcribed this just fine. Like whatever it is, I don't think it's creating a problem, but I I wanted to run some experiments where I was essentially filtering out types based on some criteria, like maybe the least frequent types or the highest entropy types or something like that. And I would guess probably that that's a high entropy type. Actually, I looked at it and it was about 2 bits of entropy, which was more than many of the types, but also not anywhere near the most entropic of them. Which, yeah, I would need to look a lot closer. This was with the Spire tokenizer, by the way, not one of the ones that I trained specifically. So this is the one that I know works better than any of the ones I trained recently, but I don't know why. Yeah.
No other question?
Mhm.
Thanks a lot, man.
Thank you.